All right, welcome everybody. So to start class today, whether you're in school or out of school, we're going to be doing the same thing. So if you can get your Unit 2 packet out and open to page 16 and take these notes as I go through it. And then hopefully after today's video, some misconceptions that we had on the quiz should be clarified. And I'll point out some of the specific reasons why I awarded some points back on the quiz, some stuff that we didn't cover beforehand, and I'm sorry for that. I'm sure that added some stress, and that was not what I meant to do. It's just we got a lot going on right now. We're all going to make mistakes. All right, so hopefully you guys forgive me. We can continue to move on. Some of you that did not do so well, I'll try to come up with some sort of redemption assignment where you can do some more of these volume, pressure, temperature problems to earn some points back and get another good grade in this Unit 2 part of the grade book. All right, so without further ado, let's get started with notes on page 16. And we're going to be talking about phase changes at first. All right, so this some of the stuff might seem a little bit like a review after you did a little bit of your own research for the crossword puzzle, and some of the stuff I'm sure you've known for years and years. All right, so first of all, take a look at this diagram here. We have solid on the left, liquid in the middle, and gas on the right. So when we absorb energy into a substance, right, or a substance absorbs energy, molecules are starting to speed up, right? Energy is absorbed when we are increasing in temperature. So going from solid to liquid to gas as we increase temperature. And as we decrease temperature and energy, right, we're going from a gas to a liquid to a solid. All right, I'm sure that's elementary to you. All right, so almost all substances can exist as solids, liquids, or gases. Some more prevalent in a certain phase based on the conditions that we have here on Earth. But under the correct conditions with changes in temperature and pressure, we can get different phases for different substances. So if somebody asks you if you have some water, right, what phase are you automatically thinking? Are you automatically thinking, right, liquid phase? Because that is not specific enough. Right? Now, what if I said I had water at 32 degrees Celsius? What phase would that be in? Okay, so if water freezes at 0 degrees Celsius and water boils at 100 degrees Celsius, well, at 32 degrees Celsius, it would be liquid water. All right, so in this class, we are going to have to specify whether we mean solid water, which would be ice, liquid water, or gaseous water or water vapor. All right, so your phase is going to depend on the temperature and pressure and the attractive forces between the particles. There's a demo that we were going to do before I had to teach from home for a little. But what we can do is if we put a beaker of water in the bell jar that we had in class, we decrease the pressure of the surrounding of that water, we can actually make that water boil at 40 degrees Celsius. That's 60 degrees below the typical boiling point of water. Right? And as a substance gains kinetic energy or temperature, it will change phases. Right? It will go from solid to liquid and then from liquid to gas. Or in some instances, it could even go right from a solid to a gas, and we'll talk about that in this video. Alrighty, so just the generic order here, we can go from Bose-Einstein condensate. Remember I said that was just theoretical, to a solid, then liquid, to gas, and plasma, right? Because plasma we know has the most energy, even more so than a gas. Alright, so just some questions here. This is not in your notes. So what happens if you reduce the volume, right, of this container? Right, would there be no change other than the atoms would be closer together? Right, will more atoms condense? Right, and we'll talk about what condensing is in a second. Or will more atoms evaporate? Alright, so take your best guess here. It doesn't have to be correct. Alrighty, so a little bit more here. But a little bit of the nano view of what's happening at our three states of matter. So as substances can exist as solid, liquid, or gas, they are referred to as solids, liquids, or gases, right? The three states of matter. And all substances we know are made of tiny particles, right? Atoms or molecules. And if we're looking at a solid, right, we have a fixed, right, set pattern, and they would vibrate in place. Right? As we heat it, it would turn into a liquid. Right? Particles start to free flow over each other. Right? They would still have that same volume, but the shape would then change, right? Because the connection between those molecules is not as strong, right? And they're moving faster, so they're allowed to separate just a little bit. And then when we get to a gas, right, these are very far apart. They move very quick, right? A lot of times we say they're bouncing off the walls. And that would have referred to one of your questions on the quiz was what happens when you heat up an enclosed container, right? As we heat up the inside of that container, right, the gaseous particles on the inside start to move faster. And as they move faster, the collisions between themselves and the collisions between themselves and the walls of the container, right, are more forceful, causing the pressure to increase. All right, so at the bottom of page 16, let's take these notes right here. So as I go from a solid to a liquid, this is nothing new, this is melting. As we go from a liquid to solid, we call it freezing. So you can write this above or below the arrows. It's tough to see if you write this inside the arrows, so I don't recommend that. All right. And two ones that might not be as commonly known, but I'm sure some of you are aware of. So as we go from a liquid to a gas, we call that evaporation. And when we go from a gas to a liquid, we call that condensation. Right, so evaporation happens all the time. You ever wonder why liquid water after rain, like a puddle, just disappears the next day? It's because the sun will evaporate that water into the gaseous form, and it will, right, disappear from the sidewalk or driveway or wherever you have it. Condensation happens every morning or night when you take a shower and you get out and your mirror is all fogged up. It's because that water vapor that was in the air during a shower, once it came into contact with the mirror, it cooled down and went back to the liquid phase, or went right from gas to a liquid, yes. This also happens if you have like a water bottle outside on a hot summer day and it starts to sweat. Right, that's condensation. The water vapor from the outside air is cooling down when it collides with your water bottle, right? And you see those little beads of water on the outside. All right, now these next two are brand new. I doubt that you've ever come across them before the crossword puzzle, so I would definitely put a star next to these terms. You would be asked these on a Unit 2 exam. So as we go from a solid to a gas, we call this sublimation. And I always remember this one because, right, it starts as a solid, which starts with an S, right, and sublimation starts with an S. And the reverse of this, when we go straight from a gas to a solid, is called deposition. I don't have a unique mnemonic device for that one, I'm sorry. All right, so let's talk about some examples here. So some common examples for sublimation, right, when we change from a gas to a solid, right, would be freezer burn. If you've ever had something in the freezer that got that frost over top of it, what actually happened was some of the water vapor in the air around you was trapped in the freezer after you opened and closed it. It cooled so rapidly that it actually skipped the liquid form. It went straight from a gas to a solid. That's why freezer burn ice looks different than the ice that you might have in your ice cube tray. Some other examples would be like moth crystals. If you ever have some clothing in storage and you put some mothballs in there to make sure that nothing's going to happen to your clothing. Right, it goes straight from a solid to a gas, and that gas prevents moths from being attracted to your clothing. Dry ice is another perfect example. If we set some dry ice out on your desk, right, it would disappear over the course of a class period, but no puddle will be left behind. And Mr. Arrow and myself will be doing a dry ice demo with a pumpkin once I'm back in school, sometime around Halloween. Not that I won't be back until Halloween. I will be back next Wednesday, so I will see you guys at the end of next week. One commonly missed question on the quiz, the States of Matter quiz, and rightfully missed because we did not cover this in class, is what is the most dense phase of matter for water? So I awarded everybody that point back. So if you got it right, that was a bonus point for you. If you got it wrong, you were not penalized. But I do want to talk a little bit about water and how it is the exception. So if we have something like methanol, if we have a solid block and we would put it into a liquid container of methanol, right, both the same substance, what do you think would happen? Would it float? Would it sink, or is it just going to hang midway through? All right. Well, we were supposed to have a nice animation there. I'm sorry. But what would happen with methanol, and like with most substances, is that solid would sink to the bottom because solids are the most dense phase of matter for most substances. Now, water is the exception. We know when we put solid water, ice in our liquid water, right, the ice floats. So why is that? All right, so as water molecules cool down, right, they settle into this nice crystalline shape. And this shape, right, creates little pockets of emptiness. And these little pockets of emptiness cause solid water to actually be less dense than liquid water, one of the only exceptions to this rule. All right, so again, I'm sorry for a question that you weren't prepared for, but you will not be penalized for it. And some of you that got it right got a bonus point. So there we go. All right, I want you to take a quick second and answer these 5 questions, these 5 true or false questions, and then hit continue, and you will see the answers and you can check your work. All right, welcome back. So I want to do a practice problem similar to one of the ones that you had on your quiz. So we have a basketball inflated to a pressure of 465.4 mmHg at a temperature, and I changed the temperature to 25 degrees Celsius. If the basketball can withstand a pressure of 1,580 mmHg before it bursts, what temperature would we need to heat it up to before it blows up? Right? In this scenario, volume is staying the same. Right? And then we want our answer in degrees Celsius. So I'll start with my T-chart. All right, my temperature 1, or my pressure 1, is 465.4 mmHg. All right, my temperature 1 equals 25 degrees Celsius. My pressure 2 is 1,580 mmHg, and my temperature 2 is unknown. All right, so first thing I need to do is I need to convert my temperature 1, right, to Kelvin, and this is the step that a lot of people missed. So I will do my 25 degrees Celsius plus 273 to give me 298 Kelvin. It's my new temperature 1. All right, and now we need to rearrange our formula to solve for T2, and this is where a lot of people missed some points on the quiz, was with rearranging our formula. So let's start with our formula of P1 over T1 equals P2 over T2, and I need to solve for T2. Now, I can't move P2 over. There's nothing I can do to move P2 over. So what I'm going to start with is I'm going to start with cross multiplying. So this will give me P1 times T2 equals P2 times T1. All right. Now we can easily solve for T2 by dividing both sides by P1. All right, and the P1s will cancel out on the left. All right. And now I can plug my information in. Ta-da! Right? Magic. So in this instance, our units of millimeters mercury will cancel out, giving me just units of Kelvin. All right. And when I type this into my calculator, I should get 1,012 degrees Kelvin. Now we are not done because we wanted our answer in Celsius. I could not leave my temperature in Celsius through the problem because I would have got the wrong answer, but I can convert back at the end. So in order to get this back to Celsius, all I need to do is subtract 273, and I should get 739 degrees Celsius as my final answer. Alrighty. So, right, one of the main things you need to remember when doing these problems is whenever we're using temperature, even if it's asking for units of Celsius at the end, you always need to use Kelvin in the formulas. Alright? And then when solving for something in your denominator, right, you can't just move your numerator over to the other side. We need to use cross multiplication. Alrighty. So that's the end of this video. Have a great rest of your class. I will see you